Today, we explore a beautiful subtlety in queuing theory. When the population is finite, the very act of joining a queue removes a potential source of future arrivals. Imagine n users. Each is either idle, thinking and occasionally generating a job, or already inside the system, waiting or being served. Watch what happens as users move into the system. Each one that joins is one fewer source of new arrivals. The pool of potential arrivals shrinks. This is the core of state-dependent arrivals. If k users are inside the system, then n minus k remain idle. By the superposition of independent exponential clocks, the total arrival rate is simply their sum. Here, beta is the rate at which a single idle user generates a job. Lambda sub k is the aggregate rate when the system holds k customers. Let us draw the Markov chain for n equals 5. The states 0 through 5 count how many users are currently in the system. Look carefully at the forward rates. They are not constant. They decrease as we move right. From state 0, all 5 users are idle, so arrivals come in at rate 5 beta. At state 4, only 1 user is idle, and the rate is just beta. Service happens at constant rate mu, pulling customers back down the chain. Notice the chain naturally terminates at state n. There simply cannot be more customers than users in the world. Let us solve a concrete example. A help desk has 3 users, 1 server, and 1 buffer slot, giving capacity 2. Each idle user generates work at rate 2, and service rate is 4. We compute the arrival rates. Lambda 0 equals 3 beta, which is 6. Lambda 1 equals 2 beta, which is 4. And lambda 2 equals beta, just 2, but these arrivals are blocked since the system is full. When we apply the cut method, slicing between states 0 and 1 6p0 equals 4p1. And between states 1 and 2, 4p1 equals 4p2. Normalizing, so probabilities sum to 1 yields p0 equals 1/4, and p1 and p2 each equal 3/8. Now comes the most delicate step. When arrival rates depend on state, the blocking probability is not simply p sub L. We must weight each state by its arrival rate. Why? Because the rate of attempts to enter depends on how many idle users remain. Plugging in our numbers, the numerator counts blocked arrivals per unit time. The denominator counts all attempted arrivals. When the blocking probability is 1/4. Notice this is smaller than p sub 2, which was 3/8. That is the self-regulation at work. The effective throughput sums arrival rates only over states where arrivals can actually enter, that is, states 0 through L-1. When we get 3 customers per unit time effectively entering the system. The mean number in system is 9/8. Finally, Little's law delivers the mean time in system, 3/8 of a time unit. Let us crystallize what we have learned. In a finite population, every customer inside the system silences one source of arrivals. The arrival rate decreases linearly with the number of customers, and the state space is automatically capped at n. And because rates differ across states, we must weight by them when computing blocking, probability, and effective throughput. This is the system gracefully regulating itself.